First of all, I would like to thank the organizers for putting together this amazing event. We've seen so many exciting talks. I'm going to talk today about our work on adaptive quantum annealing using weak measurements. This work was done primarily by two postdoctoral fellows in our group in Waterloo, Edward Tang and Salil Betkihal. This is a collaboration with the group at UC Berkeley, in particular Song Jiang, Juan Atalay, and Birgitta Whaley. And the work is done as part of the QEO program, so I'd like to acknowledge support by the program and also lots of inspiring discussions with everybody in QEO. So we are interested in quantum annealing. So the task at hand is the usual one. We want to prepare the ground state of an easy Hamiltonian H0, and then deform this Hamiltonian adiabatically into a problem Hamiltonian HP, whose ground state contains the solution to a hard optimization problem. This graph here shows the ground and first excited state energy levels versus this annealing parameter S. And a big problem in quantum annealing is what happens around the minimum gap, which arises in as these problems get more difficult. So around this minimum energy level splitting, it's getting much harder to preserve adiabaticity. And this, of course, is a problem at the core of quantum annealing, and there are various takes on this problem. One idea is to use optimized schedules, so it makes sense to think of slowing down just around this region here where the gap is small. In general, the problem with this approach is that you can do this, but you need to know some prior knowledge of the energy spectrum, which is itself a hard problem. And then there are also some other solutions that were proposed which don't obviously scale up. I also want to mention that there is a strong connection between what I'm going to discuss today and what was presented by Michael Jarrett yesterday, where he discussed an approach of doing adaptive annealing based on an estimation of the gap that has to come with certain properties. So in this talk, we are taking a bit of a different perspective on this. I would say it's definitely a more physically motivated picture. And in fact, we hope to understand the connection with this scheme in more depth in the future. Also, I want to say that this work is closely related to work done at USC by Kawai Heap et al., where a similar protocol has been presented at the March meeting recently. So to deal with this problem of annealing, we want to rely on the measurement of ground state curvature. So this starts with a simple observation that was already made in this paper by Wilson et al. In 2012, that if you look at the ground state of a system during annealing, so the ground state versus annealing parameter is shown by this curve here. The annealing parameter is called lambda here, just a different notation, so I'm going to use that notation from their paper. So if you look at the ground state versus lambda, where you have the minimum gap, there is this fast change in the slope, hence the curvature has a maximum right at that point. So if you have a way to know what the curvature is, you can purposely slow down the annealing around the minimum gap point. And in this paper, they did an analysis where, assuming that they had perfect knowledge of the curvature, so assuming that this quantity, the second derivative of the ground state energy with respect to the annealing parameter, was perfectly known, they showed that you could make annealing more efficient by adapting the annealing speed. So we are taking the similar approach, but what we are trying to do is understand one essential point in this protocol. So this paper did not address specifically how to get this information on the curvature. It was assumed based on existing superconducting devices that you could measure the curvature with superconducting circuits, and in fact you can. But when you think about this as being a proper quantum system, what you need is to really take into account a full quantum measurement model. So you need to specify what operator you are going to measure, how you are going to measure it, and also take into account noise and back action. And this is what we are trying to do here. So one first important question to tackle is the maximum curvature a good proxy for the minimum gap? And of course, what I show so far relies on this on this picture that when you have an anti-crossing, there is a large curvature, of course. But this it's not entirely obvious that we have to look at regions of minimum gaps as being determined only by these two lowest lying states. So we did a numerical study where we looked at the proximity between the minimum gap of a given instance. So here this shows the energy gap G between the ground and the first excited state as a function of the annealing parameter S. So we looked at the proximity of the minimum gap point to the value of the curvature is maximum. Now, even if these 2 points do not coincide, they have to be close enough. And close enough in this case here, we took that to be a bit of an ad hoc definition. And so we defined this gap with delta based on this condition that the energy is smaller than 2G minimum. So in an annealing schedule, we look on the one hand at the energy gap shown in black here versus S, and on the other hand at the curvature shown in blue here. And we want to analyze this difference between SG star, the minimum energy gap, and SK star, the maximum curvature. We did this for random instances at this point. So we took 10,000 random instances. The initial Hamiltonian is the usual transverse field Hamiltonian. And these results here show this relative proximity of the 2 points, SG star and SK star. And this is again relative to the gap width. So for instances with 4, 6, and 8 qubits, we see that this relative proximity is really very good. Most values are close to 0, and many of the values are below 2 or so. So this is encouraging. Again, it's an analysis we have to extend, take into account more look at larger number of qubits. And as I will say towards the end of my talk, we also need to understand this using more analytical approaches. Now, as I mentioned at the beginning of the talk, a big motivation here was to really identify a proper procedure to do a quantum measurement of this spin system. So when you think about measurements, you need to talk, of course, about the operator that we are going to measure. And thinking about this problem, we came to the conclusion that a good operator to measure, which is a good proxy for the curvature, is this commutator of the problem on the initial Hamiltonian with 1 over I in front. So when you look at the expectation value of this operator in the ground state, in the adiabatic limit, this is related to the curvature of the spectrum. And here again, just to validate that it's a good idea to measure this operator, we looked at the relative proximity defined in the same way as before. So here again, for a given instance, in black is the minimum gap versus annealing parameter. Blue is the expectation value of this operator in the ground state. And these 3 panels here show for 4, 6, and 8 qubits and a set of random instances. They show the relative proximity of the expectation value of this operator C and the point of minimum gap. Again, the proximity is fairly good in all of these 3 cases. Finally, it's also interesting to think about the transition probability, which is determined by this transition strength, so the matrix element of the derivative of the Hamiltonian with respect to the annealing parameter between the ground and excited state of the many spin system. And here as well, we see that there is good proximity between the minimum gap, the minimum gap point and the point where we have the maximum transition strength. So next we want to use this to test numerically an adaptive annealing protocol. So we have this operator that we want to measure. This operator is in a relation with this curvature here of the ground state energy, which is given by this relation here. This is based on the Pechuka-Sukawa formalism. And another aspect we have to keep in mind is the total transition probability between the ground state of the many spin system. So using adiabatic perturbation theory, this is given by this expression over here, which is related to this expression for the curvature. And based on this connection, we propose to change the annealing speed in a way which is proportional to the expectation value of the operator C. This seems at least to be a good starting point, but we are still in the process of possibly improving this. So once we have this, we do a model of the annealing protocol based on the stochastic Schrodinger equation. This is the wave function of the system, which evolves due to the Hamiltonian H. S of t is the annealing schedule. C is the operator that is measured. This equation is stochastic because the measurement results are random, so the randomness goes in through this dW quantity over here. The feedback is done by changing the annealing speed, as shown here. So the annealing speed is proportional to the instantaneous value of the curvature with the running time average. So this shows an example of the application of this approach to an 8-qubit instance. So again, we take a random instance where the H and J parameters are between -1 and 1. This graph here shows the energy levels as a function of the annealing parameter. There is a point with a minimum gap here at around s equals 0.3. If we run this adaptive annealing schedule, as shown here by this blue curve, the S parameter over this total time, 150 in energy units, this annealing schedule shows that indeed slowing down occurs in the region of this minimum gap here. So once we have a large value of the quadrature, annealing slows down. For comparison, we can take this time to run the adaptive annealing protocol and run a simple linear schedule without any measurement and feedback. And if we look at the ground state probability in the course of annealing with the adaptive protocol shown here and without the adaptive protocol in place, we see that the ground state probability is preserved much better when the adaptive annealing protocol is used. We started a statistical analysis of the improvement you are getting, which is still in progress. But for now, looking again at 8-qubit instances, we get results that are summarized in these graphs here. So here, this axis is the minimum gap. So the minimum gap relative to the transverse, to the initial transverse field. It goes from 0.04 to 0.2 here. As this minimum gap gets smaller and smaller, the time to solution, which is the good metric to analyze this, the time to solution shows a larger and larger advantage compared to linear to the linear schedule. Right. So with this, I'm going to close this part, which again focused on a series of arguments combined with numerical experiments. And I want to talk a bit about how we hope to move towards a more in-depth understanding based on analytical approaches. So there are several key questions here. The first is whether the two-level approximation holds in those regions where the gap is small. What is the right proxy for the transition rate? So we have good evidence that this curvature operator is a good quantity to look at, but we are thinking of whether there are maybe other approaches. And also, can we look at generic models that describe hard annealing problems? So for now, at least as a starting point, we decided to adopt the random matrix theory because it has the appeal that it gives you a model which seems to apply universally to many body problems. We can get analytical results out of this. And there's already been work in quantum annealing using random matrix theory. So I want to mention this paper. And also there is a talk by Itai Hen today. So now there are things are quite tricky. It's actually hard to tell whether RMT is a good model. This is never an easy answer. Then, assuming that RMT holds, can we design annealing schedules based on RMT? And also, the ambitious goal here would be to analyze scalability in this framework. So the random matrix theory was discovered, motivated by the question of understanding the spectrum of complex many-body physics, starting with nuclear physics. There are two, when you look at the energy level splitting in a complex many-body system, there are two extremes to this. One is when the energy levels are uncorrelated, so then you get a Poisson distribution. The other extreme is when these energy levels are strongly correlated, and the energy level statistics is given by this function here, conjectured by Wigner. So in the analysis we did so far, we look at the nearest neighbor spacing distribution as a measure of spectral regularity. So we want to be in this limit where RMT holds, and the nearest level distribution gives an indication of that. To do that, we use the Braudy probability distribution, which interpolates smoothly between the Poisson limit and irregular spectrum limit. And this approach has already been used in this paper here. So in this paper, this Braudy distribution was used for a FreeSat problem, and at least in that case, it was found that a large value of the Q parameter is indicative of harder instances. Now, once you have RMT in place, and once you assume it works, you can use it to get, at least in a statistical sense, measures of transition probabilities between a given energy eigenstate and other eigenstates of the system. So in the analysis we did so far for random instances, we looked at this Braudy parameter along an annealing schedule. So here the annealing parameter S goes from 0 to 1. And we find that over a fairly large region of this annealing schedule, the Braudy parameter is large. And this is indicative that RMT may be a good description to look at this. And once we have RMT in place, again, this allows one to get expressions for the transition probability, for ground state curvature, and all of that. And we are working through this at this point. Okay, so again, this seems promising. At least again, so when you think about getting anything that is even close to analytical, or in the perspective of getting scaling behavior of this protocol, it definitely seems like a hard problem. So we hope at least that RMT comes with a set of tools that would give us some insight into this. But there will likely be better approaches than this. Last, I just want to mention briefly that we started looking at open system dynamics as well. So everything you've seen so far focused on the closed system picture. We started for now in implementing a numerical approach where basically instead of solving the stochastic Schrodinger equation, we solve the stochastic master equation, where again the ingredient is you look at the deterministic evolution, but in addition to this, you bring in terms that describe the coherence. And we have some preliminary results that show to us at least that for these sizes at the scale of several qubits, typical decoherence rates, at least relaxation rates, don't seem to be a problem. But there is a lot of work that we need to do to close in on this question. And of course, looking at the open system case will be even harder. So with this, I would like to summarize. I presented adaptive annealing protocol based on continuous measurements. We did a numerical analysis of this protocol using the stochastic Schrodinger equation with feedback. We find for up to 10, 15 qubits or so that there is an advantage for many random instances. We also started an analysis of adaptive annealing using RMT. And next, we are interested in optimizing this protocol. There are many things we can think about here. So you can change the feedback functions. You can also think about measuring other operators. One thing I didn't discuss much is the structure of this curvature operator, which in fact is implementable with phase-slip qubits, but still looks like a very difficult task. So we are interested in finding out whether there are better operators, easier operators to measure. Next, we also want to look at applying this protocol to specific problems, so not to random instances, but actual relevant optimization problems. We started this already. Of course, the big prize is scalability, and we hope at least that with RMT we start to get some insight, and then we also want to open. We want to continue open system dynamics work, where there will be some tricky points once you start to think about the small gap limit and so on. And with this, I would like to again acknowledge support in the QEO program and the amazing collaboration with everyone there. Also mention briefly that we have a postdoctoral position open in Waterloo. And yes, thank you for your attention.
Can you go back to the stuff on about slide 6, where you're looking at the percentage of ones where you got a good correlation? So you got you were talking about 4, 6, and 8 qubits, and you're looking at how well whatever it was you were measuring there was correlating with the minimum gap.
Yeah.
I'm just worried about how that's scaling, because those are small numbers, and you can either have finite size effects in there, or it was going down anyway.
Yeah, indeed.
So
Yeah.
I think that's what you're aiming to fix by doing the random matrix theory, but I'd just like to, that was the thing that worried me about that. It was
absolutely. So we will have to extend this work and try to really understand these. And really try to understand these trends. Of course, numerics will be part of the answer once we've gone through this more systematically. Then again, we really have to think about what really happens. Maybe use RMT, but we don't even. I mean, I wouldn't say that there is a scaling law yet at this level. Also, maybe we need to check a bit better numerical precision issues as well, which of course become harder and harder as you increase n. So yeah. So unfortunately, I don't have a good answer to this.
How do you envision actually measuring this curvature operator in a physical system, say a network of superconducting flux qubits?
Yeah. So so this commutator will be a sum of single sigma y operators and products of sigma y and sigma z operators if you use the X transverse field as the initial Hamiltonian. This is possible with phase-lit qubits. So this can be implemented using magnetic measurements, basically. So you can measure magnetic moment corresponding to the sigma y operator, and we also have an approach to measure products of Pauli operators as long as they can be connected with magnetic moments. So that part seems doable. Of course, there are scalability issues that we need to understand as well. So there is the problem that you have a large sum of these operators as you increase the system size, and so again, it's a scaling issue that we need to understand. So if you make a magnetic detector that is larger, the response time will be reduced. On the other hand, for large problems, we do expect the time to get longer as well. So things might get even, but it's a detailed analysis that really has to be pursued there. Yeah, and if anybody has idea about measuring other types of operators, we'll be really happy to discuss this as well. So.
I have one question. So about your measurement of curvature. So this makes sense when you have a single annealing parameter, right? Yeah. But when you go to having freedom with both, how you change an annealing schedule for the initial Hamiltonian as well as the problem Hamiltonian, then in those cases you don't necessarily need to satisfy these curvature conditions. So have you thought about sort of how you would sort of extend this to the more generic control scenario?
I mean, we thought about it, but not we didn't really analyze this because I think there is still so much to understand in more depth here. But we are interested in this for sure. Yeah, looking at multi-parameter schedules. In principle, if this works with a single parameter, I mean that would be the best case scenario, right? If it works, then you don't even need to think about multi-parameter schedules. It's of course a big if, but yeah, that's why I want to focus on this at this point. So, yeah.
I have a question about the calculation of the curvature. So calculation of the curvature is as hard as calculation of the spectral gap. Is that an approximation, 1/I HPHO? Can you describe that one?
Yeah,
in
yeah. So
detail for me?
you mean the correspondence between the second order derivative of the energy, of the ground state energy, and the expectation value of this operator? That's yeah. So it is an approximation. In that it requires for adiabatic evolution to hold. So now one part here, and that's why we did these numerical experiments to confirm that C is a good proxy, is that as you proceed with the evolution, at some point the adiabaticity will start to break down, of course. But at the same time, if you get a strong enough indication of the value of C before you get into the gap region, that should be good enough. It's not even a problem actually whether you completely destroy the case, that's fine, because you can always redo the schedule. That's basically no cost, right? But as long as this wake monitoring procedure works reasonably well, then it's fine to redo the schedule. But yeah, that's a good point. It has to be firmed up, and again, it calls for an analytical approach.
Thank you. Thank you very much.